Today, we want to keep talking about double integrals. Remember the big idea. We're trying to find the volume under a surface f of xy and above a region R that's sitting in the xy plane. The region R is just a bunch of coordinates xy that we're plugging into the expression f of xy dA and then adding up the results. I know it's super fishy to say we're adding up the results because we're adding up over a continuum. And where are we going to put the plus sign on a continuum? But that's what we have the fundamental theorem of calculus for. That's what antiderivatives are for. Our job right now is to take what we understand and take the process that we already understand and adapt it to this function of two variables and figuring out how to tell the integral what we want to plug in. And to that end, we want to describe the region R with the two statements, what's x between and what's y between. This is what we want to be able to do. So we're going to split our double integral into two integrals, either a dy dx or a dx dy. And we're just going to do this in pieces. We're going to start off by describing what x or y is between, and then we're going to integrate, finish that out, and then we're going to describe what x or what y or x is between. The other one is between. So we're really just doing one integral with what's x between, one integral with what's y between. Now, there are rules to this. The early integrals, so the first integral that we're going to do, can use functions of the upcoming variable. So in a dy dx integral, the boundary, the interval for y, can use functions of x as your, let's see, it's y, so your bottom and the top. But the outer integral only gets to use constants. So the outer integral only gets to use constants. So what happens is we have a function of x's and y's. We integrate with respect to y. Then we plug in functions of x wherever we see a y. Now we've got just a function of x. And so now we have a single integral from a to b of some function of x dx. So this part takes care of the y parts. So it's okay for the early integrals to use functions of upcoming variables, but the outer integral only gets to use constants. Oh. So last time we took this rectangle where y goes from 0 to 3. So we just started breaking up this rectangle in a bunch of different ways, where y goes from 0 to 3 and x goes from 0 to 9. We started off with just a rectangle, and then we made a triangle from 0, 0 to 9, 3, and then we made another triangle from 0, 3 to 9, 0. Today, we want to break it up into a different function, and you will see that it's all going to be the same kind of thing. It's always just going to be the same stuff. So yeah, last time we connected 0, 0, this corner 0, 0 to this corner 9, 3 with just a line. Now I'm just going to bend the line a little bit. And I'm going to put in a parabola. So let's suppose that this is the parabola. Looks like I wrote y equals square root x. So that, instead of a line, we're going to have a parabola, y equals square root of x. Now, we know we're going to be writing two integrals. I know we've only had one day of me doing this, but every single time I make you write two integrals, so we're going to be writing two integrals. That means we're going to want to turn this around. If y equals the square root of x, then that means x equals y squared. So depending on how we want to describe the parabola, whether we're making a function of x or a function of y, we got these two descriptions for the parabola. Now I got to tell you which part of the region I want. It divides this rectangle into two not quite equal regions. Let's start with the one above. Let's suppose that the region R is the upper part. And we're going to write two double integrals to describe this region. So we're going to write a dy dx integral, and we're also going to write a dx dy integral. One thing to note is that on my integrals, I always write x equals and y equals. That is to remind myself which one goes where, because we're new. Once we're old pros at this and we've done thousands of problems, so like Thursday, you don't need to write the x and y. It's understood that this first integral is going to be a dy, and this last integral will be the dx. So you don't need to write the x's and y's, but right now we're new, so we're going to remind ourselves that of which one goes inside and which one goes outside. But the dy dx or the dx dy, that will tell you which one is which. But we're new, so we're going to write it. It's like when you're new at algebra and you write 5x minus 4x, you write 1x. You don't need to write the 1, but you do at the beginning to understand that it's one of those x's. Question? Yes. Yes. This is just a way of describing shapes. That's kind of the technology that we have. All of the single integrals where you calculated area, we can describe those with a double integral. And we would just integrate the function 1. When you integrate the function 1, you get the length over, when you integrate the function 1 dx, you get the length of the integral. When you integrate the function 1 dA, you get the area of the region R. Because if we have length and width and height, if one of those is equal to 1, then your area and your volume will have the same value. There'll be different units, because area will be in square meters and volume will be in cubic meters, but they'll have the same value. So, whenever we're doing this, the easiest thing to do, since the outer integral only gets to use constants, we always fill in the outer integral first. So in our dy dx integral, we're going to go from 0 to 9. We don't get to use a function. We just have to write the lowest x value and then the highest x value. That's the easy parts. Now for the y's, we pick a typical x value, and we go up until we get to the lowest value in the region. So here the region starts at the parabola and ends at 3. So I'm describing these y values. We start at the parabola and end at 3.
Why did you put the square root of x on the bottom of the y integral?
So that's our process. You do the outer integral first because it's always constants. Then you go for a typical, since it was x, for a typical x value, where's the lowest y? Where does the region start vertically? Where does the region end vertically? And then you just turn that sideways for the other integral. So for a dx dy, since dy is our outer integral, we only get to use constants. So y goes from 0 to 3. We don't worry about anything being all bendy. We're just describing the lowest and the highest y values. We're about to describe the bendy parts with the x's. So for the dx part of the integral, we pick a typical y value, and we get the lowest x and the highest x. Here, the region starts off at 0 when x is equal to 0 and ends at the parabola.
Oh, why did you put y squared?
And here are two double integrals for some function over this region. Cool. As far as the calculation of the integral goes, we already know how to do that. It's just going to be the antiderivative version of partial derivatives that we've already done. So let's say, for example, I wanted to calculate over the region R, this region up here, the integral of something simple. Let's say 2x dA. So I'm just saying f of xy equals 2x. We have these two double integrals to describe what's going on. I could write this as the integral from 0 to 9, then the integral from root x to 3 of 2x dy dx. Here's more like what we would write. We wouldn't include the x equals and the y equals. Because we're advanced now. We spent a whole day on this. A whole day plus 10 minutes, that's like almost an hour. We should be professionals by now, right? Isn't that how it works? Maybe. So in this case, the first integral we come across is this dy integral. So we integrate 2x with respect to y. So I haven't done anything with this x integral. So the integral of 2x with respect to y is 2xy. Then we evaluate from root x to 3. Now remember, the root x and the 3, those are going in for the y. So this will end with a function of x. We're still integrating with respect to x. We haven't done that yet. So we have 2x times 3 minus 2x times the square root of x dx. Now we've got just a function of x. Our double integral went to a single integral, and our single integral will go to a constant. So let's clean this up. This is 6x minus 2x to the 3 halves. So now we're going to integrate with respect to x. The integral of 6x with respect to x is 6 halves x cubed, or x squared. And then x to the 5 halves. To the 3 over 2. So we add 1 to the exponent, 5 halves, and times 2/5, so minus 4/5. And now that we've integrated, we can evaluate from 0 to 9. So we plug in the 9, 3 times 9 squared, minus 4/5 times x to the, 9, 5 halves. Minus 3 times 0 squared, minus 4/5 times 0 to the 5 halves. So we'll have 3 times, friggin' arithmetic. 9 squared is 81. Is that right? 81, 3 81s is 243. Thank you. Minus 4/5 of, let's do the square root of 9, which is 3. 3 to the 5th is 81 is 243. Is that right? And that makes sense. So it must be because here's 243 minus 4/5 of the 243. That'll give us a 243 over 5. So 9 to the 5 halves. First, we'll do the square root of 9. That's 3. And 3 to the 5th is 243. Do the denominator first to make things smaller. Square root of 9 is 3. And then do the 3 to the 5th. Yeah, there's no trick to it. Uh-huh. Yeah. Yes. Yes, because it's gonna be simpler on the dx integral. Because if you thought you were getting out of doing that one, then that's just not how this works. It's not how any of this works. I can't leave an integral undone. I even had to cram this up into this corner here without working this out like down as like notes, because I didn't want to go to a whole nother line, because I think I could fit this second integral down here. Let's find out. So if we integrate 0 to 3, this one is definitely more appealing as far as if we had to pick one, because they both have a 0 involved. That's a great point. It's like, if we have to pick one, the one with all the zeros in it, especially when it's like polynomials. If we start throwing trig functions and whatnot, then maybe the zeros might not be as good. But what we want to notice here is that our first integral is a dx integral. So in the previous problem, we integrated 2x with respect to y to get 2xy. Here, we're integrating 2x with respect to x. So that's going to give us an x squared. So we're going to go from 0 to 3 of x squared evaluated from 0 to y squared dy. So already this one is better. It starts off with a 0 and there's no square roots in it. Sign me up. So we're going to have the integral from 0 to 3 of y squared squared minus 0 squared. All the x's went away, leaving us with this dy integral. So that's good. This is going to be a y to the 4th. So when we integrate, we get a 1/5. There's the 1/5. I'm starting to be very confident now. Y to the 5th evaluated from 0 to 3. And there's our 3 to the 5th. We got the same thing for both double integrals, so that's a pretty good indication that we are correct. Not a guarantee, it's just good evidence. Any questions? Yes. Yes, you can have multiple layers and you don't even have to do any substitution trickery. Remember that up here, we're dealing with double integrals, and I didn't say first and second. I said early ones and outer ones. This is because I think tomorrow we're going to have a third integral. There's going to be an x, a y, and a z. And so that first integral, let's suppose it's a z and there's x and y. Your interval for z can have functions of x and y, upcoming variables. Your second integral, if it's y, let's say, that one only gets to use x, and your x will only get to use constants. So your early integrals get to use functions of upcoming variables. Your outer integral only gets to use constants. But yeah, we can have triple integrals where we're describing, instead of integrating a function over a region, we're integrating a function over a solid in three-dimensional space. Any other questions? Is everybody okay? It's gonna be next. I was actually gonna change up the region. It's a little dented in. How about some scale? Zero, so x and 6 minus x, so 0 and 6. Okay, that's what complication did I include in describing this region? What's the complication that I included in describing this region? More than one term of x. So I gave you a function, y, I wrote y as a function of x, but y is not an invertible function of x. So not only more than one x term, the x squared and the x, we're looking at a range of x's on which this function is not invertible. So that's the curve that I gave you on this one. If we're going to write two double integrals, this is where we run into a problem. The function is not invertible. But it's a parabola, so I'm still keeping it simple. Let's write down the easy integral to write down. So here we have our x goes from 0 to 6. Our rectangle has y equals 0 to y equals 9. For the purposes of writing our double integral, it doesn't matter what the function is, so we'll just call it f at xy. The more convenient integral for us is to use dy dx, because x is going to be more complicated to describe than y. Y is just the regular description. So I want dy, since y goes from 0 to negative x squared plus 6x. Then our dx just needs to go from 0 to 6. This is the easy double integral. If your task is to just write a double integral, this is the one that you want to write. Not just because it's easier, but because if I ask you to write a double integral, I want you to write the easier one. The whole point is taking the path of least resistance. If I want you to write the other integral, then I'll say just write both. Give me both double integrals. If you write the more complicated one, you're trying to flex. I'm not going to be impressed. It's like, well, why are you making more work for yourself? Every time you make more work for yourself, you increase the probability that you make a mistake. Play it safe. Just go for the layup. But I'm going to ask for both because this is not just scoring points. This is a contest. This is a dunk contest. And we want to make sure that in an integral fight, we can not just win, but dunk on our opponents. That's most important. Now, here's the problem. Our function, as we can see, is not invertible. If this one is nice and simple. For a typical x value, we go from 0 to 6. The y starts off at 0 and ends at the function. No problem. But when we try to go the other direction, we pick a typical y and we get two different x values. Each y corresponds to two different x values. That's what makes this function not invertible. In this case, there's no trick to it. It's just a simple trick. Question? That's a good question. Could we just do this to the halfway part and double it? That would be an excellent strategy. We can write two different functions. We can write x as two different functions of y, from the left to the middle, and then from the middle to the right, and then just add the two. Could we not take those two integrals, just pick one of them and double it? Could we take those two integrals and just double one of them? Remember, this is not this specific one. This is not specific. Under what conditions could we just double our result? That's a great question because no one has an answer. So now you can tell what question I will not be answering today. It's that one. Under what conditions could we just double the results? And why is that going to be okay? All right, let's move on and let's write a double integral for this one because writing two integrals, great solution, would totally work. But let's be fancy. Here's what I want to do. The problem that we're running into is that this has two instances of x, but it's a parabola. And so this standard form is trash. Standard form of a parabola, trash form of a parabola. We should write it in vertex form because then x appears only once and we can invert it, kind of. So I don't want this in standard form. I'm going to write it in vertex form. And the vertex is at 3, 9. There's our vertex at 3, 9. If you like, you can complete the square. But if you're doing Calc 3, you're not going to flex on anybody by doing algebra. Better to just write down the vertex form. And now, those of you playing along at home, you could see, you could see as well, you picked the easiest non-invertible function that I could pick. Well, yeah, because it's the first example, so don't at me. I'll do cosine on the next one, or I'll do sine on the next one. Then it'll be more exciting. What I'm talking about? Now that I've got only one instance of the variable, I can just do inverse operations in reverse order. This is easier to invert. So here I can say x. Let's see. I just need to solve this for x. So I'll subtract 9. I don't know if I can do it not in pieces. It's Monday. Then divide by -1. And then square root. Now here is where we get to the non-invertible part. Because if I take the square root of both sides in the process of solving, that produces a plus or a minus. Now I'm writing two functions, but they both have very similar forms. Then I can add 3 to both sides. Everybody okay with the algebraic sleight of hand? Nothing up my sleeves. I suppose if I want to convince you that I'm not trying to fool you, I shouldn't dress like an amateur magician, but oh well. So notice what our original problem was. We had two x's. Let's call them x1 and x2. Also notice the form of the function we got. And then we can arrive at the actual point of me doing this example. To further convince you that the quadratic formula is trash and that we should always be confusing this way. Because if you look at the form of our functions, 3 plus or minus the square root of 9 minus y. 3 is what's in the middle. And we either plus the square root of 9 minus y or subtract the square root of 9 minus y. So our x1 must be where we subtracted the square root of 9 minus y. And our other x must be 3 plus the square root of 9 minus y. By writing it in its vertex form, we identify where the middle is. And so it's easy to invert. So if we integrate dx first, we're going to integrate from the lowest x value, which will be 3 minus the square root of 9 minus y, and we'll integrate up to 3 plus the square root of 9 minus y. For dy, we're just integrating constants from 0 to 9. We had to find out where the middle was because we got symmetry around the 3. But we raised a great question. Under what conditions could we just double the 0 to 3? Or f of y, g of y. Under what conditions on the function f of xy can we just stop at 3 and double? So instead of going from, let's say, 3 minus root 9 minus y to 3 plus root 9 minus y, just go 3 minus root 9 minus y and stop at 3 instead of going that extra distance. Think about the conditions. What would f of xy have to look like for us to be able to do that? We'll have to do some science, or y'all will have to do some science on that. Make a hypothesis, try it, see if it will work. So a similar thing can happen. This was about finding the middle. A similar thing can happen if, let's say, we have something what is not a parabola. But let's suppose that our function was y equals sine x. Here we would want to do the same thing. We might notice that there is a sine inverse button sitting right on our calculator. So you might be thinking, dude, sine is invertible. And it's true, sine is invertible, but not on this interval. Sine is invertible on the interval from negative pi over 2 to pi over 2. This is the interval from 0 to pi. So this is the interval. I don't know why I have so much y-axis down here. I don't know why I'm so obsessed with how much y-axis I have under here. I could just write x equals 0 lower. Well, apparently I cannot. So we have a similar issue. Sine x is not invertible on the interval from 0 to pi. We have a sine inverse function, but that stops at pi over 2. Your upper and your vertical ones, your y would be from 0 to 1. But we're going to have to do something else for our x integral. Because the same thing happens. For a typical y value, we come across two different x values. Oh, it's like a Cylons are coming to get us. Does anybody know what a Cylon is? One person. I just need one person to know what the hell a Cylon is. Then I'll be okay. Not quite Doctor Who. Doctor Who adjacent. I love how television is not okay with certain words. Like you can't say fuck, but if you just trade it for something else and like crack, they're like, oh, okay, that's fine. It's fine. Yeah. Holy shit. No, you can't say that. Oh, holy dren. Acceptable. Everybody knows what the word is that you replace. Yeah. Yeah. And see, the wise parent knows that their kid learns swear words and knows the swear words. And you just teach the kid, it's like, oh, you know what? I don't like hearing the swear words from you. When you're with your friends, swear all you want because you're not going to police each other. When adults are around, these are words you don't get to use. I remember the first time my goddaughter swore in front of us. She was testing us out. We were like driving the car, come back from the movie. And she said something like, I think she used S because it's safer than an F-bomb. But he's like, oh, that was a bunch of shit. And we were driving in the car, and my friend and I looked at each other and go, acceptable? You are old enough. You may use the swears in front of the adults, but not your mother. So we're good. So that's just how it works. All right. Figure out where the middle is and figure out how to integrate in this style, even though we don't have to always. That's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.